All right, so a couple announcements. Almost put your coat on to come inside today. Probably the last day for that. You might have gotten an email from the Class Advising Center about a winter test prep course. So I just wanted to advertise that again. If you will be taking the MCAT or the, I don't even know, PCAT, other entrance exams this year, there's a course that they give in class. It meets like once a week. It starts in January and it only costs like $60, something like that. So just advertising that resource is available. Go on the Class Advising website and you should be able to find a link to that. They are also offering 5 Kaplan course scholarships. So if you are taking the MCAT this year, I know from experience in my family that was a really helpful thing. It's very expensive though, so check that out. The deadline to apply for that scholarship is December 1st, so that's coming up. Check that out if you're interested. Okay, any of you pay attention to the news? Yesterday, there was a big announcement from Pfizer. They think their vaccine is 90% effective. So I'm really excited about that. That's way higher than what we had projected. There's lots of other vaccines in the pipeline. So that dovetails really nicely what we're talking about right now. And we're going to talk all about COVID vaccines next week. So read about that in preparation if you want, if you're interested. But kind of really exciting. It's a new vaccine. We don't have any vaccines right now that are in use that are messenger RNA vaccines. So we'll talk more about that next week. So last time we got through most of our innate immunity, chapter 15. I wanted to throw up a practice question about complements, which is probably one of the more complicated aspects of innate immunity. A lot of you have said to me, oh, I've had some of this in other classes. This is looking all a little familiar, the cells and things, but I wanted to throw up a complement question. So say a patient is unable to synthesize complement protein C8. How will this impact the function of her complement cascade? So I don't know if I'll give you a little chance, we'll just read through it together. The complement cascade wouldn't be activated. No opsonization, but activation of inflammation and membrane attack complex would be functional. No inflammation, but opsonization and MAC would be functional. Opsonization would result, but not inflammation or interferon production. We haven't even talked about that yet. No formation of membrane attack complex, but opsonization and inflammation would be functional. Okay, that's the correct answer there. Part E, complement protein C8 is one of the, it's C6, C7, C8, and C9 that form the membrane attack complex. So, a little practice there. Again, if you look at your learning objectives, I've written actually a whole paragraph kind of summarizing complement there. So check there for specifics on what I'm hoping you to learn about complement. All right, so let's continue. We've mentioned inflammation a few times. Now I get to be kind of more direct in what that I'm talking about there. If you haven't had any experience learning about inflammation, in your homework includes a 4.5 video tutor. It's one of those Dr. Bauman's video tutors, which are very good. So basically he explains all this in 4.5 minutes really clearly. I would encourage you to, as you're watching animations for your homework, don't zip through those as fast as you can. Take some time. I think the animations are really good to help the concepts sink in a little bit. All right, so we often think of inflammation as being a bad thing, but of course it's our you know, programmed by our immune system to be helpful. So hopefully you'll understand a little bit better how inflammation helps us. Of course, it can go on too long and then it's detrimental. But we're going to show how it helps to mobilize and attract immune components, so cells complement to the site of injury, how it helps kind of keep localized, like keep things in one spot, as well as clear harmful substrates like toxins, for example. It's absolutely a necessary thing before our tissues can heal and regenerate. Some of the symptoms of inflammation you've probably seen. Here's a picture there that will give you a hint of some toes that are really badly inflamed. So redness, localized heat, pain, unfortunately, and swelling, which we also refer to as edema. All right, so this condition here, usually these symptoms come about as a result of some kind of injury or infection. In this case, this is a picture of someone with chilblains, which is a reaction to cold temperatures. The toes swell up, they get really red, they get actually kind of itchy as well, but it can be very painful. So that's kind of an exception, not something that's really, I guess you could argue that the cold in some people is causing the damage. Inflammation can be acute. That's when it's acting for our benefit. Again, it can go on too long and be chronic and then that is not good. Then we want to try to do things that's going to suppress that inflammation. All right, so what triggers inflammation? Well, we talked about complement last time. Those two fragments, C5A, remember we said A, think allergy, inflammation, chemotaxis, C3A. Those complement fragments during that cascade bind to some granulocytes. Remember, our granulocytes are neutrophils, basophils, eosinophils, cause them to degranulate. So let loose their granules. What's in those granules? Well, inflammatory mediators. Okay, I'll talk about a couple other examples of inflammatory mediators, but probably the one that's most recognizable to people is histamine. Okay, what do you do when you have a cold? You take an antihistamine to try to suppress kind of the fluids, the mucus production, the pain, the swelling. Okay, so that histamine release and other inflammatory mediators is going to trigger dilation and increased permeability of blood vessels. We're going to see a close-up of that in a second. Okay, which that increased permeability of the blood vessels is going to increase the movements and we'll say migration. Phagocytes, so they can get to the sites of the infection or injury, and hopefully that leads more quickly to the resolution of the infection, or brings about healing to the injury. Okay. All right, so we look at a close-up there of the capillary bed. Let me go back a second. Yeah. Okay, so if we look at the capillary bed after there's been some kind of injury or response to a pathogen. Normally, this is what it would look like, the blood flow between the arteries and the veins. And if there is some kind of injury, typically those blood vessels are going to very briefly constrict, just to kind of keep someone from bleeding out, perhaps. But then soon after that, we get the release of these inflammatory mediators that are going to cause the capillaries to dilate. All right, so we call this vasodilation. Okay, and that means so the capillaries are getting larger and they get leaky. Okay. All right. And so again, looking at a little bit closer that process, that increased vascular permeability. So normally we get a little bit of movement of fluid through this interstitial space. The spaces between the cells here, it's pretty tight. So we call that interstitial space between the cells is pretty tight, but we get a little fluid, you know, some gases, nutrients that are normally leaving the blood vessel. But typically the cells are going to, for the most part, stay in the blood vessel. Of course, the red blood cells, they always stay there. We don't want them leaving the blood vessel, but here's a cell like a monocyte. Remember, the monocytes differentiate into phagocytes and dendritic cells when they leave the blood vessel. They're just flowing through the bloodstream. When we have the presence of these inflammatory mediators, the blood vessel gets larger and the space between the cells gets larger as well. So we have more fluid leaving, and cells are also going to be leaving that blood vessel wall through a very complex process, actually. First, those cells have to slow down and stick to the side of the blood vessel wall. All right, so we call that process margination. So the process by which white blood cells adhere to the sides of the blood vessel wall. And like I said, that's actually a very complex process. There's 8 or 9 different signals that have to be satisfied, receptors that have to find the right match for that process to take place, because we want to make sure that it's appropriate for the cell to be doing that. So that's actually margination, a complex process. It's only when they slow down and stick, though, that then they're able to leave the blood vessel. So the process by which the white blood cells then actually leave or migrate into the tissues, we call that diapedesis. Okay, so margination first and then diapedesis. They're migrating through the blood vessel walls so that those white blood cells can get to the site of where, again, the pathogen is. Okay. All right, so then we start to kind of understand those effects of inflammation, why we feel those. Okay, we get redness and heat because of that increased blood flow. The pain is a result of basic couple things, cytokines acting on nerves, as well as the compression on the nerves due to the swelling. So unfortunately, inflammation can be a fairly uncomfortable thing. And the edema, this is more, the swelling we see is because more fluid is leaving the blood vessels out into the tissues. Okay, so what good does that swelling do? It helps dilute any virulence factors released by the pathogens. So things like toxins get diluted, extracellular enzymes get diluted, antiphagocytic factors. It can bring proteins to the site if it's an injury and clotting is necessary. Of course, we get a better chemotaxis of cells. They're flowing in that fluid rather than having to move in a amoeboid motion themselves. So macrophages, neutrophils, where the infection's taking place. And it lasts a long time. Now that can be a good thing. It can be, again, a not such a good thing. But it does give cells time to get to the area. Okay, and I think about, well, my daughter gets allergy shots. We see all these things. So her arm gets warm, it's red, it swells up a little bit. It's probably a little bit painful as well. And I got to thinking as well, it's very common for athletes when, that's sort of the dogma. You run a hard workout, go get in an ice tub. It will help your muscles recover. Obviously, when you have an injury, right, you try to get the swelling down because it's usually too much swelling, more than what we need. But is this really a good idea after a hard workout to help you just recover to sit in an ice bath? And I was reading some articles that say, no, that's absolutely the wrong thing to do. That there's been some studies done that actually that slows down the beneficial effects of inflammation. We do that when we ice, it slows down the blood flow to an area. And basically it just delays the inflammation taking place. So it's kind of an interesting thing to research a little bit. Don't argue with your trainer too much, but maybe, look into it yourself if that's something that you commonly do. Okay. All right, so again, that's inflammation. There's a great animation there in your homework to review that a little bit. Another consequence of inflammation can be fever. All right, and why do we spike a fever? Well, there's something that's acting as a pyrogen in our system. So that prefix pyro, that means heat inducing. Okay, so a fever-inducing chemical, it's acting on the hypothalamus deep in our brain. That's our kind of thermostat for our body. So these pyrogens act on the hypothalamus to raise our internal temperature a little bit. What kind of things act as pyrogens? Usually some kind of cytokine. I won't get too specific there. Ideally, those cytokines are acting in kind of a controlled way, and we'll talk about some of the benefits of how that fever can help us. Sometimes parts of pathogens will act as pyrogens, and then it can be in a very kind of out of control type of way. So endotoxin, for example, can act as a pyrogen itself. It also can stimulate cytokines to act as pyrogens. What good does the fever do us? Well, it probably inhibits, or it has the potential to inhibit the growth of pathogens. Now, actually, in terms of bacteria, your body temperature is going up, say, a few degrees. Most bacteria, as we understand now, have a pretty wide range of temperatures that they grow at. So typically a few degrees is not going to make that much of a difference in terms of bacteria anyway. So that benefit is a little bit tenuous. It does stimulate our immune system in general. So basically higher temps, faster reactions. So in terms of increasing phagocyte activity or mobility of white blood cells. Okay, so speeds up And that definitely, we think that that definitely is a benefit to fever. So that's pretty well documented, no matter what the pathogen is. You kind of goose our immune system a little bit to work a little bit faster. We know that fever signals cells to take up any available iron. So it impedes nutrient availability of pathogens, specifically that iron availability. So we talked about that a little bit with our first line of defense. A lot of our fluids in our body have some chemicals that will kind of take up iron, sequester iron to try to keep that pathogens from utilizing that. Okay, so there are some potential benefits here. So the question is, when you're ill, say you have a temperature of maybe 100, 101, is it good to just let that fever go, or do you want to take some Tylenol or ibuprofen to try to suppress it? And that's a little bit controversial. If you have a high temperature, 103, 104, yes, get that temperature down, because it gets much higher than that, and that's bad. But generally, the consensus is that if you have a low fever, the discomfort that fever causes probably outweighs any of these benefits. Like, the benefits are probably pretty minimal. So it's okay to go ahead and take some Tylenol or whatever your choice if you have a fever. I admit that I was that mom when my kids were little, to just kind of let them sit and ride out the fever, let them rest a little bit. Obviously, you don't want to give aspirin to kids because of potential of Reye's syndrome, a brain, I don't know if it's infection exactly, inflammation maybe. Fever certainly is very important as a barometer to try to understand that, yes, there's a problem here, there's an infection. So, with babies or, people that don't communicate very well, to understand, oh, there's a fever, there's something going on, there's an infection here. It's definitely helpful in that way. Okay. And of course, if you do have a fever, you should be fever-free for 24 hours without drugs to suppress that fever before you go back to class or work or whatever. A lot of times we try to kind of talk our way out of that. All right, so we're most of the way through our second line of defense here. We've talked about different cells like granulocytes, agranulocytes, complement, inflammation, and fever. Couple more things I just want to mention as we wrap up here: our innate immune system. And that's just a few words here talking about cytokines. And this is the exact kind of slide that they say teachers are not supposed to have, like one that has, a ton of information on there. My goal for this slide is just to talk generally about cytokines, what they are, and I want you to understand some examples of cytokines. Okay, so tumor necrosis factor, yeah, that's an example of a cytokine. That's pretty much all I want you to know. I want to talk about a little bit about what they do, just because it's kind of interesting, and that can kind of help you remember a little bit. So what are cytokines? I've used that word a bunch already. They're kind of non-specific protein mediators. They're signals. They act as intercellular messages, activate lymphocytes, and lots of specific immune responses. So I've said that we're pretty much talking about cytokines in general. We're not worrying about which cytokine does what in most cases. A lot of cytokines have the name interleukins. So that's kind of the old-fashioned name. Like when I took immunology, we used the term interleukins. So we had IL-1, IL-2. There's like 36 ILs, and a lot of them have overlapping function. We understand now, though, that these proteins don't just act between white blood cells. They act on a lot of different kinds of cells, even blood vessels, for example. So we decided that that's not a great name for them. But they, were so popular, we kept the name, but we said, okay, interleukins are an example of a cytokine, basically. So we kind of made this other umbrella term above that. And this is just an example of what a couple of cytokines do. Don't memorize that. Tumor necrosis factor is another cytokine. We named it tumor necrosis factor because we found that in mice, it actually worked to break up tumors. And this was first discovered, got really excited, hey, we found the cure to cancer. But when they injected it into cancer patients to try to break up their tumors, it caused just galloping inflammation. And one thing I forgot to mention about inflammation, when your blood vessels get too leaky, get too big and too leaky, you get too much fluid leaving your blood vessels, your blood pressure can go way down. That's a condition known as shock. Okay, your organs can rapidly shut down when that happens, and that can be life-threatening. So again, too much inflammation is a really bad thing. So they found that that was not good for a cancer cure, again, because it caused this overwhelming inflammation. And there are some autoimmune diseases where the drugs that we take for them are actually tumor necrosis factor blockers. So you've probably seen the Humira commercials for rheumatoid arthritis. It's used to treat Crohn's disease. They try to block this particular cytokine. So again, we don't have this inappropriate immune response. And there's cytokines that act to release inflammatory mediators. So I talked about how complement fragments can release inflammatory mediators. Also, cytokines can act on cells to do that. So here's some more examples of inflammatory mediators: bradykinin, prostaglandins, leukotrienes. Just kind of recognize those as how these are inflammatory mediators. It's complicated, like what actual macromolecules some of them are lipids, some of them are proteins, some of them are a combination of those things. And lastly, I'm just going to mention briefly the action of interferons. I used to go into a little bit more depth about how they work. Basically, there's several different kinds of interferons. The alpha and the beta interferons are important. It's one of our innate system's only mechanisms to try to slow viral infections. And interferons actually act on cells to slow down protein synthesis. So the virus can't synthesize their own proteins. Okay, so I used to go that in more detail. The objective that I have in your learning objectives, I have an objective for that. And just know that interferon can slow down viral infections somewhat. Okay, and there's actually different kinds of interferon. Interferon gamma has a totally different mechanism, different purpose. So don't worry about like what that is, because we're not going to talk about that any further. Okay, and then just to wrap up, there's a nice table in your book. Some of you on your exam questions, you know all the details, but then you don't understand the big picture of things. So you're missing some questions there. So this is just kind of a summary of our innate system, split into the first line and the second line. And pretty much we talked about all those things. So don't miss the general picture as well as the specifics. All right, questions. I would definitely encourage you to start working on that chapter 15 homework if you haven't already. Okay, so just a step back again where we're at. This is chapter 15, the innate system. We're ready to plunge into chapter 16 and talk about our adaptive immunity. So how do we get these super specific responses? Okay, that's going to involve B cells and T cells. We also want to understand first a little bit about our anatomy and where some of these immune reactions are taking place. We'll talk about antigens as well, try to kind of piece together so we finally, next time, hopefully we'll get to how B cells and T cells get activated. Okay, so again, we're going to start with some anatomy here, which probably a lot of you know better than me. What makes a good antigen? Remember, an antigen is something that stimulates an immune response. Basic structure of antibodies and what they actually do. When a cell is infected by a virus that's inside the cell, how do we have immune cells that recognize that a cell is infected? There's a mechanism for cells to advertise that. So we're going to go all through that, how T cells do their killing, how B cells, remember B cells are the ones that make antibody, how they get activated to make antibody. So that will mostly take us through, again, the rest of today and next time, and maybe into next week as well. An overview of adaptive immunity. So again, this is our body's way to recognize distinct invaders. So if we look at some attributes of adaptive immunity compared to innate immunity, I thought it would be easier to write in the word rather than the definition. Specificity is a hallmark. Basically, we have these B cell and T cell receptors for almost any type of antigen that we might encounter. We have millions of different ones, so we can have a very specific response. And actually, we don't make them when we encounter the pathogen. We already have them, a few, and then those few cells proliferate, basically. So we activate the cells only when they're needed. So we call that inducibility. So we only have a few of those cells, and again, those get called into action when the need arises, and they make many more of themselves. So we call that clonality. Okay. Those particular cells that are needed, again, make lots and lots. We make lots and lots of them. When our immune system is working as it should be, it's unresponsive to self. I thought that was kind of self-explanatory, but we have mechanisms in place to keep our immune system from firing on our own cells. We'll talk a little bit about how that works. Okay. And big one here, memory. All right, the next time that same pathogen is encountered, we don't have to go to all the trouble to activate our response. Those memory cells are ready to go and ready to act. Okay, so the next time we encounter a pathogen, the response is a lot faster. So that's the basis of vaccines, getting memory cells. All right, so the cells that are important here, we've mentioned them already. Okay, basically adaptive immunity mostly involves our lymphocytes, our B cells. They are responsible for our antibody immune response. Sometimes we call this a humoral response. Our body humors are our fluids. Okay, so antibodies are mostly in the bloodstream. They're in mucous membranes, things like that as well. These antibodies are going to act on extracellular pathogens. Okay, so our antibodies don't do a lot of good for viruses or bacteria that are inside our cells. They don't have the mechanisms to notice that. Okay. T cells, on the other hand, we call this a cell-mediated immunity. Several different kinds of T cells that mediate that. And they are better at acting on intracellular pathogens. Okay, so especially viruses. Okay, there's some bacteria that live intracellularly as well, like mycobacterium that causes tuberculosis, or chlamydia is another intracellular pathogen, but viruses are a good example there. Okay. All right, so the lymphatic system. Where are these lymphocytes, B cells and T cells, making the correct interactions with pathogen and different kinds of antigen? Well, we have primary lymphoid organs, and that's where lymphocytes are made. So the two primary lymphoid organs, bone marrow and the thymus. Okay, so in the bone marrow, B and T cells are made. And this is not in every bone. It's mostly your like bigger, flatter bones like your femur, in your hip, I believe. Here's a picture there, red bone marrow. Okay, so B and T cells are made in the bone marrow, and B cells mature here. Okay, so think about what that means, mature. I always think of that Cheez-It commercial, you know, they gotta let their cheese mature, and what that means. So when a B cell is maturing, that means they're differentiating, they're getting the correct B cell receptors. T cells differentiate into different kinds of T cells, as well as, you know, getting their appropriate T cell receptors. So that's a little bit of what I mean by maturing. Okay, and then in the thymus is where the T cells mature. Okay, so we're going to talk a little bit later what exactly goes on in the thymus, but this is a little gland near our heart. Does most of its work before we're even born, during fetal development. Okay, secondary lymphoid organs there, where lymphocytes become activated. So this is where B cells and T cells are mostly coming into contact with the pathogens that they need to mount a response to. So we have lots of lymph nodes. We have somewhere between 500 to 700 lymph nodes in our body, strategically placed. We have lots of them, especially in our neck, armpits, and groin. But this is where a lot of these immune reactions are taking place. The lymph is filtered a little bit. Macrophages and dendritic cells, remember, one of their primary functions is to process and present antigen. So they're presenting their antigen to B and T cells here in the lymph nodes. Spleen is another part of another considered a secondary lymphoid organ. Its primary purpose, though, is to filter the blood and not the lymph. We can get by without a spleen. So you may know somebody that, you know, had an accident and their spleen ruptured. Apparently, you can't just sew a spleen closed. You have to just remove it. Some of our other secondary lymphoid organs kind of take over the function of the spleen a little bit. But if you don't have a spleen, you're a little bit more susceptible to certain kinds of infections. You might need to go on antibiotics prophylactically. Like if you know you've been around somebody with a kind of infection, they might put you on antibiotics more often. You might have to take more vaccines than other people. Tonsils, again, we can certainly do without our tonsils. They are just lymph nodes, basically in the back of our throat. Sometimes they get too many craters in them, and people actually get more likely to have infections when their tonsils are there. I know that I had mine out when I was 35, and I'm a lot better without them, so good riddance. Okay, so they function the same as lymph nodes. And then there's this tissue that we abbreviate MALT, mucosal associated lymphoid tissue. So we've got this MALT tissue associated with all of our mucosal membranes Remember, we have a lot of those. The ones in our intestine, we have the special name here, the Peyer's patches. Okay, and so that's mucosal associated lymphoid tissue that its job is to sample inside of our intestine. It's checking for foodborne pathogens. Okay. So that's Peyer's patches. So again, all those are considered secondary lymphoid organs. Okay. So we do, if you think about that's our lymphatic system, what actually is lymph and where is it coming from and where does it go and what's it made out of? Our lymphatic capillaries are associated very closely with our blood capillaries. And we talked about what kind of things, even when we don't have an infection, what kind of things leave the blood vessel wall. We got things like gases being exchanged, of course, nutrients leaving to get out to tissues. We got some fluid, some water. Okay, all those things are constantly kind of leaking out of blood vessels into the tissues. And when the pressure in the tissues is greater than what's in the lymphatic vessels, some of that fluid will flow back into our lymphatic capillaries. Okay, and they will flow through our lymphatic capillaries in one direction. There are some valves here to make sure that it only goes in one direction, and it flows towards the heart. Okay, we don't have a lymph pump, right, like we have the heart. So how does it flow? Well, it moves more slowly than blood, but it's by muscle action. So we have some smooth muscles. When you move your skeleton muscles, that probably helps move your lymph around a little bit quicker as well. So, you know, sitting for a while, okay, got to get my lymph moving again. It's going to help me fight infection. Why not? So lymph travels to the heart and then to the place in our blood vessels where our blood pressure is the lowest. I believe it's the vena cava. Wait, let me read that again. Like I said, my anatomy is not as good as probably yours all is. I think it's the vena cava. I might be wrong about that, but the blood vessels where your blood pressure is lowest, that's where your lymph dumps back into your blood system. Okay, to travel around again. All right, so these lymphatic capillaries, okay, they will eventually come to a lymph node. So it's cross section of a lymph node from your book here. And first thing that I will point out is that there's 3 different afferent lymphatic vessels. Oh, actually 4. Okay, so there's 4 afferent lymphatic vessels. A means towards. Okay, so lymph traveling towards a lymph node. And we only have 1 efferent, so away, lymph traveling away. So that doesn't seem very efficient, but that's by design because you want the lymph to stay in that lymph node for a little while. It's kind of a bottleneck. 4 ways in, only 1 way out. So it forces the lymph to kind of circulate around the lymph node. And that's where, again, we've got our, say, macrophages with antigen that it needs help with, presenting to B cells and T cells here, kind of a lymphoid party here, lymphoid coffee house, where you're making connections with lots of, you know, other cells. Okay, so the lymphocytes, B and T cells are traveling in the lymph. We've got some lymphocytes in our blood as well. So we've got mixing with the blood here. Okay, and that's where like a B cell with a B cell receptor that's specific for some pathogen is going to find that pathogen. Okay, so that's why our adaptive immune system takes a while to mount a response. It takes a while to make all the correct interactions to find the pathogen that it needs to be, that it matches up with. Okay, we know that sometimes our lymph nodes get larger. Okay, that's one of the things that your doctor might check for in your neck. Are your lymph nodes swelled up? Okay, that's a sign that there's some kind of infection going on. We get more fluid, more cells, and they tend to swell up. Question? Yes, okay, you're right, there is two, you're right. So the question is, it shows two efferent vessels. Okay, yeah, you're right, there's actually two leaving there. Still more coming in than what there is leaving. Okay. All right, so we've got kind of the where in kind of a general way things are happening. We need to talk a little bit more specifically about antigens, some terminology to do with antigens, and kind of understanding a little bit more about them. So antigens are, like I said before, molecules the body recognizes, or the immune system recognizes as foreign. Okay, and they elicit an immune response. So sometimes I have people say to me, I can't keep straight which is the good thing, which is a bad thing, antigen, antibody. Okay, antigen are antibody generators. All right, so that's why they're named antigens. That comes from the root antibody generators. So they are causing antibodies to be generated, okay, when our immune system is working as it should. Okay, so some examples of antigens are things that can act as antigen, various bacterial components, especially proteins, viruses, fungi, protozoa. Something doesn't have to be organic to be an antigen. Things like food. If you've got a food allergy, then food is acting as an antigen. Dust, or like I said, the feces of dust mites can certainly act as an antigen. You might be allergic to cat dander. Something like that can definitely function as antigenic particles. Okay, so to be a little bit more specific, an epitope then, this is a region of an antigen that's recognized. Okay, so for example, this picture is a little bit helpful. You know, the whole bacteria cell can be considered an antigen, but then specifically say what our antibodies might recognize, they might recognize different epitopes. There would be many different epitopes that might be recognized by our immune system. So many different patterns, for example. Okay. These are also known as antigenic determinants. Right. Okay, so I think maybe your book uses that term in a few places. Antigenic determinants, basically they determine, you know, what our immune system recognizes. I usually use the word epitopes. Okay. All right, so what makes a good antigen? So what I'm asking there is, what kind of molecule, what are the attributes of it that would make that molecule elicit a strong immune response? Okay, that's the question that we have to ask when we're making vaccines. What part of that pathogen is going to be most important to elicit a strong immune response so that we have memory to it the next time? Okay, so things we need to consider, shape. Okay, a molecule that has a very distinct 3D shape is going to be more likely to be recognized by our immune system. The size is a big one. Okay, larger molecules are more easily recognized. Generally, small ones are not recognized, but there are some exceptions there. So, for example, poison ivy oil is a very small molecule. Its molecular weight is really small. But we know that that acts as an antigen for most of us. We get, that itchy rash associated with it. But that poison ivy oil actually soaks into our skin and then complexes with the protein in our blood sera. And then that complex acts as an antigen. So poison ivy oil is an example of a hapten. Okay, it's an antigen, a very small antigen that links up with some carrier protein, and now that whole complex elicits an immune response. Okay. The other thing that makes a really good antigen is a molecule that has high complexity. So that's kind of a similar concept to shape, but if there's lots and lots of different epitopes, then it's more likely to elicit an immune response. Okay, so therefore, what kind of molecules are good antigens? Proteins. These are usually the best antigens. Here's an example of a protein. This is beta-galactosidase. That's the enzyme that cleaves lactose into glucose and galactose. Just an example of a picture of a protein. It's a big molecule. It's really complex. All those alpha helices, beta sheets, it's all bonded together to be a complex molecule. So proteins are usually going to be really good antigens. If you've got a protein complex with a lipid or a sugar, they usually are kind of mid-range. They act as antigens as well. Something like a polysaccharide that's one molecule repeated over and over and over and over again is usually poorly antigenic, but again, there are exceptions to every rule here, and we'll talk about some of those exceptions. This is an example of starch. Okay, glucose, 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 many glucoses. Okay, not complex at all. It can be a large molecule, but it's just kind of simple. So most of the time, that's poorly antigenic as a rule. But again, there are exceptions to that. All right, we have some terminology as to types of antigens that our immune system encounters. Okay, exogenous antigens. I might have used that term already. Exogenous means it comes from outside of the cell. Okay, so they entered the body from the outside. So they've come through some portal of entry, we've swallowed it or inhaled it or whatever. So bacteria, viruses start out exogenous. Okay, but then once they enter our cell, they would be considered endogenous. Okay, our immune system has different strategy in dealing with exogenous versus endogenous antigens. So they are inside the cell, okay, by some protein maybe that the virus produces inside of our cells. Another example of an endogenous antigen is some antigen that's only present in some members of the species. So we call those alloantigens. And the only example that I could think of, and maybe there are others, is the blood typing. Okay, so if you have type A blood, you have these A antigens, proteins on the outside of your cells. If you have type B blood, then you have different antigens. You have B antigens. So that if somebody with A blood, gets some B blood by accident, they're going to have an immune response to that. Okay, because there's some variability within the species there. Okay. And then, of course, we have autoantigens. So these are antigenic particles that are not normally antigenic, but something has gone wrong, and now suddenly our immune system is kind of lost its immune tolerance and acting against something within our own body. Okay, so again, that causes autoimmune infections like rheumatoid arthritis, MS, lupus. You probably think of a lot of other ones. Okay, so either because of some genetic defect or predisposition or some environmental factor, we've lost that immune tolerance for our self-antigens. Okay, and then I want to mention one more that's not in your book, because we're going to come back to this a few times when we talk about specific pathogens, but there are antigens that are considered super antigens. And that means that they cause a way more than what is typically seen immune response. Toxic shock syndrome toxin is considered a super antigen. We're going to talk about that infection later on. But what's going on here, I kind of, this graphic, I like it because it's going to kind of start to introduce some connections that we're going to make a little bit later. But normally, when antigen is presented to a T cell, it's done so with these specific glycoproteins called MHC. And we'll get to that in a minute. It's presenting this antigen, and typically maybe one T cell or a couple T cells that the host had would recognize that and become activated. If you have a super antigen that's being presented, more than like 20% of the host T cells recognize that. Okay, so that causes just uncontrolled inflammation when so many T cells, kind of an inappropriate amount of T cells, get stimulated all at once. You might think, oh, that's great. Then that pathogen have a lot of help to get rid of it, but too much inflammation there. Okay, so that's a kind of typical antigen versus a super antigen. Okay, how are we doing here? All right, so this is your book's graphic to just kind of illustrate those different antigens. Exogenous antigens, they're things like parts of bacteria or parts of viruses when it's outside of the cell. An endogenous antigen, here's a virus inside of the cell. It calls these on the surface, so this is one of our cells here, this is the nucleus. These surface proteins are actually parts of the virus are being presented on the surface. Okay, so it's presenting endogenous antigens. So we're going to talk about the process by how that happens. And that's why, yeah, it's on the outside of the cell, but it's considered endogenous there. And autoantigens are, again, parts of our cells that aren't typically antigenic, but they can act that way if again, something goes wrong. Okay, so normally autoantigens wouldn't elicit a response. All right, so let's talk a little bit more specifically now about B cells. And a really important part of the B cell is the B cell receptor. The B cell receptor, it's important to look at the structure a little bit more closely, because when we talk about antibodies, the antibody structure is exactly like B cell receptor. Okay, so they have a transmembrane part here, and then there's two heavy chains, higher molecular weight, and then two light chains that make up the receptor. And then the variable region on the ends, that's where they bind antibody. Okay, so here's some bacterial cell up here with a particular whatever, something on its surface that acts as an epitope. And that's what the B cell receptor, this particular one, recognizes. Okay, so again, primarily we're going to find B cells in the secondary lymphoid tissue, some in the blood as well. The malt, the lymph nodes, the spleen. This is something that's kind of mind-blowing to me. How many B cell receptors are there on each B cell? There's about 500,000 BCRs on each B cell. Okay, we draw one, but we forget there's a whole lot more than that. It's a kind of crowded place on the surface of our cells. Okay, and they all have the same specificity. Okay, so all those B cell receptors on one cell, they all recognize one thing, like stingray venom or, you know, whatever, something very specific. We're going to talk about in a little while how these variable portions, how they get to be so specific. Okay, and it seems like it would make more sense to have a B cell that had all different kinds of B cell receptors. So it would be more likely to come in contact with something that it needed to fight. But really, that doesn't make sense when you think about it, because if there was only one B cell receptor on the whole B cell that recognized something, what would be the chance that it would actually, you know, touch whatever it needed to come in contact with? And it actually, if you have one B cell receptor that recognizes this, it sends a very weak signal, just one. You actually need to have lots of B cell receptors recognizing that same epitope for that B cell to be stimulated, to send a strong enough signal. So that, when I think through that, that helps me understand how, yep, these all have the same specificity. Okay, so what do B cells do? Sorry, my phone's ringing. Okay, they are, let's talk about what they do when they're activated first, and then I'll come back to how they're activated. Basically, once they get activated, they get bigger, they divide, and they differentiate into plasma cells. Okay, and we mentioned this before. The plasma cells are what makes antibody. Some of those cells, I'm going to say sometimes here, sometimes you'll get some memory. It actually depends how it becomes activated. Okay, there's two different ways it can be activated. It can be dependent on T helper cells. And that's going to be the most common way the B cells get activated. But they can also be activated in a way that is independent of T helper cells. Okay, so they don't need T helper cells, and they are activated by the antigen itself. Okay, that way's a lot quicker, but it's not as good a response. Okay, so we're going to wait and talk about how they're activated after we talk about T cells a little bit more specifically. So stay tuned for how they're activated. But we're going to talk now. I want to show you a picture here of a plasma cell. I think this was a graphic that I showed you before when we were talking about organelles in eukaryotic cells, and how you're used to seeing a cell that has an example of every organelle in it. But really, you know, here's a cell that's specialized to do one particular thing. It's got lots and lots of the rough ER. So you know its job is to make some protein that gets secreted outside of the cell. Okay, there's some mitochondria, some Golgi to kind of package that. But this is a plasma cell. Plasma cells make about 2,000 antibodies per second. All right, so they are antibody machines. Okay, so once the B cell gets the right activation, it differentiates into a plasma cell that makes antibodies. Okay, so let's start looking at antibodies and the structure of them and the function. Okay, so a little overview of the structure here. Like I said, this should look familiar. It looks like a B cell receptor. You got the heavy chains, the light chains. We call this variable region here the fragment of, it says fragment AB. It's a fragment of antibody binding. Okay, there's a hinge region here. It's actually kind of flexible so that those, the antibody binding part can kind of, again, be a little bit flexible there to come in contact with the antigen. And then the stem region here, this stands for, FC stands for the fragment that's crystallizable. Okay, so FC region down here, this is a little bit more constant. You're going to have 1 of 5 stem fragments. So if the mu region on the gene was italicized gene fragments, if that's the fragment that's chosen, then it's going to be an IgM isotype, or that's the kind of antibody. Again, the gamma region makes an IgG. Okay, so we're going to go through those different isotypes and look at their structure and what they're good at and all that. I put up this graphic here. This is a space filling model where one of these little balls corresponds to 1 atom. So you start to sort of understand how, like a puzzle, this is only going to fit a very specific antigen. Okay. And I should mention, these are also known as immunoglobulins. Actually, an antibody is a kind of immunoglobulin, but those 2 words are used fairly synonymously. So if you see immunoglobulin, that's, again, an antibody is a kind of immunoglobulin. Okay, so here we have immunoglobulin M, immunoglobulin G, different kinds. All right, so what do antibodies actually do? We'll talk about the function before we go back to the structure, I guess. Okay, so one of the big functions here, sorry, my words got a little bit thrown around here. Our first function is neutralization. Okay, so what does that mean? That means antibodies can block adhesion molecules on the cell surface or the viral surface. Okay, so here's a bacteria, and we've got some antibodies maybe blocking the proteins or ligands that the bacteria needs to adhere to a particular kind of tissue. Here, it's the antibody sticking to maybe the viral spike proteins. Okay, so that's the most antigenic part of a virus, usually, those spike proteins. So for coronavirus, that's what we're trying to make the vaccine against, those spike proteins. If you block that, then the virus can't attach to the cells and enter the cells that it needs to. Also neutralizing something like a toxin. You get enough antibody in there, and then the toxin is not going to function. Okay, we know that antibodies can activate complement cascade. Okay, so remember, that's the classical activation when an antibody, this is not the same picture that I showed before, but it's similar to it. Here we've got some antibody binding to some antigen. That first complement protein C1 recognizes that, and then the cascade starts. Okay, so again, the stem region, the FC portion of the antibody activates that C1 complement in the classical activation pathway. It can act as an opsonin. So remember, we talked about complement fragments like C3b that can bind to a pathogen. So pseudopods can grab a hold of that pathogen and be more able to phagocytize it. Okay, so remember, anything that's an opsonin is going to increase phagocytosis. Okay, those pseudopods have receptors for that stem portion, that FC portion. So when the antibody coats the pathogen, then it can grab a hold of the antibody and be more likely to phagocytize it. Agglutination. So if something that's something that agglutinates, that means it sticks together. Okay, so the clumps are basically, big clumps are more easily noticed by other aspects of our immune system. So again, here's another good reason why you want the specificity for each side of the B cell receptor to be the same. I don't think I mentioned that before. If they're recognizing the same thing, then you get these big clumps formed. Those easily get filtered out in either the lymph nodes or the spleen. We have those great big clumps. Okay, so filtered out. The lymph nodes and the spleen. Okay, spleen, remember, if it's in the blood. And one last function that's described is this antibody-dependent cellular cytotoxicity. We usually abbreviate that, lots of abbreviations here. But this involves a natural killer lymphocyte, which I did mention before, but we haven't really talked about other than just mentioning that. The NK lymphocytes can actually recognize, again, the stem portion of antibodies, which activates the NK cell to release a couple of cytokines, granzyme, and perforin. We're going to talk about that process a little bit later because that's the same method that cytotoxic T cells use in order to kill virally infected cells. But those cytokines trigger a programmed cell death for that pathogen. Okay, so usually the antibodies are not actually acting on some pathogen to kill it itself. It's helping some other aspect of our immunity to notice that pathogen more or take care of it. Okay. So we'll just start with the first class of antibody before we finish up here. The IgM. So we have 5 different isotypes. And because they have a little different structure, some of the isotypes are a little bit better at certain functions than others. Okay, the IgM is typically the first isotype produced. Okay, so once those plasma cells, the B cells differentiate into plasma cells, they almost always start kicking out IgM antibodies. There's some exceptions to that, but that's most commonly what happens during the course of an infection. Okay, they are pentamer in circulation, so there's 5 of them all together to make one antibody. They have some disulfide bonds here between each one, and this special kind of adaptation that's called a J chain. It's a protein that's present that helps assemble those monomers into a pentamer. Okay. What kind of functions do IgM have? Well, they're really good at agglutination because there's 10 different binding sites. You get 10 different pathogens and clumping them all together. It's good at some of those other functions as well. typically kind of a small percentage of the total antibody in the blood, but that can vary for a lot of different reasons. The time in the course of infection, for example. Again, this J chain plays a role in joining those monomers together. The IgA, we'll see, also has a J chain. There is some IgM secreted out onto mucous membranes, so that J chain has some role in that. Okay, so we'll finish up with the antibodies there, and we'll get into probably T and B cell activation on Thursday. So kind of be prepared to be thinking that day. I hope you have a good day. I do have office hours right now as well.